Hi, in this video, it's a little bit of a different video. I will be going over the paper, basically. So for this video, it's going to be January 2019, International A-Levels Edexcel Chemistry exam series, Unit 4. And this is going to be Section A of Unit 4. It's the multiple choice questions. Okay, so often even in mark schemes, sometimes it's difficult to comprehend why this is the correct multiple, the choice, what the answer is. So I think it would be very useful if I gave you all the explanations behind why this is wrong and why this is right. Okay, so let's start right away. So number 1 says propanol reacts with iodine in acidic solution according to the equation. So we are given the equation of propanol reacting with iodine in the acidic solution, and we basically get all our products. So it says which method would not be suitable for obtaining the rate of this reaction. So we're basically looking at the methods that we can use to investigate rates. Okay, so first of all, we have our answer. We're going to discuss what the answer is first. So B is the answer because as the reaction proceeds, as you can see, the concentration of H plus is increasing, right? Meaning that the pH, which is equal to minus log to the base 10 of the concentration of H plus, is going to decrease, right? So if this is increasing, the pH must be decreasing, right? Because it's minus log to the base of that. And in B, it says measuring the increase in the pH of the solution. So obviously that is not going to be suitable because pH will be decreasing, okay? So let's discuss the other choices and see why they can be used. So as we have our reaction proceeding, the concentration of iodine is actually going to be decreasing, right? Because it's the reactant being used to produce products. So the brown color of iodine is going to become paler and paler as the concentration decreases until it becomes colorless, where we used all of the iodine, okay? So therefore, we can look at the rate of change of color, right? So A can be used. And when we only have reactants, the Ci bond will be present, right? Is not present, sorry, because we have propanol and we have the iodine molecule. But one of the products, we have CH3COCH2I over here. So you can, as you can see, I just drew the structure over here, and you can see that they have the Ci bond, right? So therefore, obviously, we can use C, measuring the increase in the infrared absorption for the Ci bond. And the lastly, D, it says quenching followed by titrating with sodium thiosulfate. So, so this is the explanation for infrared. And quenching, this means to stop the reaction occurring in the reaction vessel. Okay, so we're stopping it. We can do this by using an ice bath or removing catalyst or some other way appropriate for the specific reaction that you're doing. Okay. In this reaction particularly, we are using the acid catalyst, so acid solution. Basically, we can neutralize that acid so that we can quench, we can stop the reaction occurring so that we are not altering in the sample the concentration of iodine, which is going to be used to titrate using sodium thiosulfate. Okay, so we have the iodine in the sample that can be titrated with sodium thiosulfate. It's the thiosulfate ions that will react with iodine ions to produce iodide ions and S4O62-. So we particularly, this is just extra information, but you use a starch indicator, which gives a sharp color change at the end point, right? So when iodine makes contact with starch, it's dark blue-black. But when we don't have any more iodine left, then the starch indicator is just going to go colorless, right? So it's going to be a very sharp endpoint, sharp color change at the end point. And then after the titration, you can work out the volume of sodium, the thiosulfate solution you used, meaning that you can calculate the number of moles of iodine in the samples collected in different intervals. So you can use this method to see the rate of change of iodine, right? Which is the reactant. So you can investigate rate that way. Okay, so yeah, A, C, D were correct, and B was the incorrect one. So 2, for the reaction, this shown over here, it's too long to say everything, but the important bit is that they gave us the rate equation, right? The concentration of both HgCl2 and the ether dioate ion are increased by a factor of 3. The rate of reaction increases by a factor of. So we know that these two reactants are both in the rate equation, right? If one of these are at 0 order, they won't be on the rate equation, meaning that they are not going to actually affect the rate equation. I mean the rate, how fast the rate is going to be. So yeah, the rate equation tells us that the rate is first order for HgCl2 and second order for the ether dioate ion, because the ether dioate ion has the power over there, right? So it's second order. So when the HgCl2 concentration doubles, the rate is also going to double, and the ether dioate ion doubles, then the rate is going to quadruple because it's second order, right? So, but in this case, they both increase by a factor of 3, right? So our concentration of that is going to times by 3, rate is also going to be tripling, and if the ether dioate ion is increased by, the concentration of it is increased by 3, then the rate is going to be increased by 3 to the power of 2, right? So if you overall, rate is going to be increasing by 3 times 3 times 3, which is going to be 27, and which makes D the correct answer, okay? Straight to question 3. To determine the activation energy for a reaction, a graph was plotted of ln K against 1/T, where K is the rate constant. So this is just algebra. So let's just model this, this graph, plotted ln K against 1/T. So if this is just, you know, an example linear line, the equation of the line is y equals mx plus c, right? And you can tell that it's very similar to the equation, the Arrhenius equation that the question gives, ln K equals minus EA over RT plus constant. So you'll figure out that y is ln K, it's obviously on the y-axis, right? And the x is going to be 1/T, yeah? So, and obviously the c is going to be your constant, and so we're going to have the m, which is the gradient, right? And you can see that this middle bit is the mx, right? And that is equal to mx, EA minus EA over RT. And we know that x is 1/T, so I'm just going to put that into x, meaning that EA over RT is going to be the same as m over t. So m, our gradient, is just going to be minus EA over R, and which is B. Okay, so that's how you solve that question. And moving on to question 4, which is correct for standard molar entropy. So for entropy, the increasing order is going to be from solid, liquid to gas, right? From solid to liquid is going to be a slight increase, and from liquid to gas it's going to be a very big increase in entropy. Obviously, the randomness and disorder of gases is going to be a lot larger because liquids are still just moving past each other, very close to each other. And the more complex the gaseous molecule, the more disordered it is. So the entropy is going to also increase. Okay, so with that in mind, we have iron, hydrogen, and nitrogen to compare in this question. And obviously iron is a solid, it's a metal, right? While hydrogen and nitrogen are gases. So obviously iron is going to have the lowest entropy. Yeah, so that is shown by A and C. And so we need to decide whether hydrogen or nitrogen is going to have the highest entropy. So which one looks more chaotic to you, or more disordered, or having a higher entropy for you if we just look at the dot and cross diagrams? So this is basically showing all the electrons, not just the outer electrons. So yeah, the answer is pretty obvious if you draw it like this. Nitrogen is going to be more, disordered, right? So nitrogen has a higher entropy than hydrogen because it's more complex due to having more electrons. Okay, so the correct answer would be C. Okay, and was it C? Yeah, it was C. Question 5, the Haber process is used to make ammonia from nitrogen and hydrogen at 450 degrees. The temperature of the system is increased. Okay, so what kind of effect is going to have on the equilibrium? So just extra information, in the Haber process we use iron as our catalyst. So I wrote down, I first of all started to write down the Kp expression for this equilibrium as is, and we know that the forward reaction is exothermic. Okay, because the delta H says negative 92, it's negative, so it's exothermic. So when temperature increases, I know that the equilibrium will favor the endothermic reaction. So the equilibrium is going to shift left. Because obviously, if the forward reaction is exothermic, the backwards reaction is going to be the endothermic reaction. So that's why the equilibrium is going to shift left. Okay, so if we have more reactants, that is going to increase the denominator of Kp, right? So obviously the Kp value is going to decrease. Okay, so the answer is going to be A. All right, so that was that. And number 6, when magnesium hydroxide dissolves in water, the following equilibrium is established. The expression for the equilibrium constant K is, so first of all, I know that Kc, the C over here, kind of stands for the concentration. So we must exclude anything that is not aqueous. Okay, so liquids or gas or solids, we can't measure the concentration for those. Okay, so we need to exclude that, meaning that we're going to be excluding the MgOH2 solid, magnesium hydroxide salt. So the Kc is going to be Mg2 plus and just OH. Whoop, I forgot the minus sign over there. OH minus. Obviously, the OH hydroxide ion has to be squared because we have 2 moles of hydroxide ions in the equation. In the equation over here, given 2 hydroxide ions. So yeah, the answer has to be B. Right, okay, and number 7. Energy is given out when 1 mole of gaseous magnesium ions is hydrated. So yeah, we have Mg2 plus gas, the gaseous ion being hydrated, became aqueous. This is more exothermic than the corresponding value for barium ions, Ba2 plus, because so Mg2 plus and barium 2 plus both have the same 2 plus charges, right? But magnesium 2 plus has a smaller ionic radius, giving it a higher charge density, meaning its attraction for water is going to be stronger, okay? So, and stronger force of attraction formed means that the whole reaction is going to be more exothermic, right? Because exothermic is the exothermic reactions are formations of attractions, right? So meaning it's going to attract, I just made a mistake there. So the answer is going to be A. Ionic radius of Mg2 plus is less than that of barium 2 plus, because that's responsible for making the whole process exothermic. Okay, And question 8, the graph shows the yield of product in a gaseous equilibrium at different temperatures and pressures. So the forward reaction is, so on the y-axis we have the yield. So, yield is the amount of products we have, amount of the things that are on the right-hand side of the equilibrium, and temperature on the right. And we have two graphs for one graph at 200 atmospheric pressure and one graph at 400. So when the pressure increased, so from 200 to 400, the yield increased, right? And when the temperature increased, the yield also increased, right? So as you're going from here to here, the yield is increasing. So this means that there were fewer molecules on the right, and also with the temperature changes, it means that the forward reaction was endothermic. So let's see the reason behind that. So when the pressure increases, the equilibrium is going to shift so that it can bring the pressure back down again to its normal state. And we know that if the number of molecules increase, the pressure is going to increase for gases. So we want to do the opposite of that, right? So for example, if we have more molecules on the left side over here than on the right side, obviously to decrease the pressure, we're going to shift to the right, increasing the yield. So therefore, we have to have the fewer number of molecules on the right, okay? And if temperature increases, the equilibrium will shift to decrease it back down, right? So it will favor the endothermic direction, which absorbs heat energy to decrease the temperature. So if the yield is increasing, the endothermic direction should be forwards. Okay, I hope that makes sense. So therefore, D is the answer. Endothermic is the forward reaction, and there are fewer moles of gas on the right-hand side. Okay, so with these questions, honestly, just jot stuff down that what you know, and you need to have a very constructed flow of thought so that you don't confuse yourself. Okay. Question 9. An aqueous solution contains 4 grams of sodium hydroxide and 250 centimeter cubed of solution. The pH of the solution is. So first of all, they gave us Kw, which is the ionic product of water, and it's basically the concentration of H plus times by the concentration of hydroxide ions. So if you do that, basically it has to end up with 1 times 10 to the minus 14, and you know the number of moles of NaOH because you're given the mass and you're given the molar mass, which you don't have to be given, you can just calculate it, right? Because 23 plus 16 plus 1 gives you 40. So you have the number of mole of NaOH. And basically that it is in 250 centimeter cubed solution, right? So you can also calculate the concentration of sodium hydroxide, which is going to be 0.4, and that is the concentration of OH minus because sodium hydroxide is an ionic, compound, and in a solution it's going to be just completely dissociated, right? We are going to have OH minus in solution. So if we just substitute that in 0.4, we can rearrange it so that we can get the concentration of protons, okay, H plus. And we know that pH is equal to minus log to the base of 10, and the concentration of H plus, you can just put that into there and work out your pH, which is 13.602, and then on and on. And so therefore you get your answer, which is C, okay? And the next question, a solution containing HCN and KCN is a buffer. When a small amount of acid is added, the solution acts as a buffer because. So we need to get the correct explanation. But first of all, in HCN and KCN, we have H plus, K plus, and Cn minus. These are the ions inside there, right? And when H plus, the acid, comes in, it would be accepted by Cn minus, right? All the others, we have H plus and K plus in solution. They're going to repel H plus, right? Because they're all positively charged, but Cn minus is negatively charged, so they're going to attract. So he's going to accept the H plus, so Cn minus basically acting as base. and so the pH wouldn't change too much. Okay, so that is how this is going to be working. And that option, we have A, hydrogen ions in the acid combined with cyanide ions to make HCN. So let's just have a brief look on the other choices. We have hydrogen ions in the acid combined with HCN to make H2CN+. Have you ever seen anything like H2CN+? It's kind of very, very unfamiliar, so it's probably not that. And HCN dissociates to make more CN- ions. But if that happens, we're also going to get H+ as well. And this is being added, so there's no reason for that to happen, right? The hydrogen ions in the acid prevent dissociation of the HCN. Well, there are already a little bit of dissociated HCN, and kind of, but that is not the reason why it acts as a buffer, right? So yeah, buffer is trying to not change the pH so much. It resists the change in pH, okay? So question 11, when 0.1 mole of hydrogen and 0.1 mole of iodine were allowed to react according to the equation, so we have hydrogen and iodine reacting, so we get Hi. The 30% of the hydrogen was found to have been converted at equilibrium. So inside an equilibrium, it's in a sealed tube, so we have H2, I2, all, and Hi as well in the same vessel. Okay, the number of moles of each gas present at equilibrium is, so we need to first of all, I just wrote down the equation again so that I can just write down all the calculations. So first of all, initially we have 0.1 of hydrogen and 0.1 of iodine, okay? And we don't have any Hi to start with, right? Because we just put in the reactants and they're going to react to produce products, but initially we don't have products. And we know that 30% of hydrogen has reacted, okay? Meaning that that's basically 0.003 moles reacting, right? Meaning that we're going to be left with 0.007 moles of hydrogen, okay? And we know that the hydrogen and iodine is in 1-to-1 ratio. So obviously if 0.003 moles of hydrogen reacts, 0.003 moles of iodine will also react, meaning that the same amount of moles of iodine is going to be left as well, okay? Because we started with the same number of moles, 0.1, 0.1. And with the ratio in mind again, it's 1 to 2, right? So we're going to get 2 times 0.003 moles, because this is the changes happening, like the ratio 1 represents 0.003 moles, right? In this case. So we're going to get 0.002 moles of Hi being produced, okay? So in equilibrium, obviously, we're going to have these left and this produced. So therefore, the answer is going to be D, okay? Hope that was clear. And question 12, which compound can show both geometric and optical isomerism? So first of all, we know that for optical isomerism to exist, we need a chiral carbon, okay? And for geometric isomers to exist, we need a carbon-carbon double bond, and we need 2 different groups on each of the carbons, okay? If one of the carbons is just bonded to H and H, then there cannot be a geometric isomerism, right? There cannot be cis-trans. So with A and C, I can see that this carbon that is included in the carbon-carbon double bond is bonded to both, CH3 and CH3, right? It's CH3 2. So we have the same groups attached to one carbon on the carbon-carbon double bond. Okay, so A and C cannot have geometric isomerism, so A and C are not the answer. And we have D and B to consider. So I just drew out the displayed formula of D, and I could not see a chiral carbon. But with D, you can see a chiral carbon over here, right? Because if you basically, simplify this whole thing, you get C4H7, and over here is just H, we have C2H5, and over here we have CH3. Again, like you can see it from the displayed, and that's just shortened, right? This carbon is bonded to 4 different groups of atoms, okay, which makes it a chiral carbon, okay? So yeah, the answer is going to be B, okay? And the next question, 13. Which set of reagents is not suitable for the step indicated? So this is basically a reagents and conditions question for organic chemistry. You have to memorize all the reagents and conditions and catalysts, temperatures, all the conditions. So first of all, step 1, HCN and KCN. These are the nucleophilic addition reagents, right? So the nucleophile is going to be our CN minus, and we have propanol making a hydroxynitrile, so that one is correct. So unfortunately, you need to memorize this. And if you look at step 2, basically the OH group is removed, right? That is our dehydration reaction, an elimination reaction, yeah? So, and our choice B says hot ethanolic KOH. That is incorrect. For this dehydration reaction to occur, we need concentrated phosphoric acid, and sometimes concentrated sulfuric acid is also used, or alumina is also used, Al2O3, and we need heat and pressure to dehydrate this compound and remove basically a molecule of water, producing a carbon-carbon double bond. But with step 2, hot ethanolic KOH, this is the reagents and conditions required for elimination of halogenoalkanes. Okay, this is not for hydroxynitriles. Okay, so not B is incorrect. And step 3, warm aqueous sulfuric acid for the acidic hydrolysis of the nitrile into carboxylic acids. You can see that the nitrile group over here is being hydrolyzed into a carboxylic acid group over here, so that's correct. And D is esterification. Step 4, so we have the acid and we have added the methanol alcohol so that we formed an ester bond, right, with an acid catalyst usually being concentrated sulfuric acid. Okay, so that is completely fine. So the answer is going to be B. So you need to memorize all of these reactions. Okay, so question 14. The molecule shown has 3 functional groups labeled X, Y, and Z. So you can see X is we have a bromine molecule on that, so it's a halogen on there, and Z is a ketone, right? Y is an alkene group, so we have a carbon-carbon double bond. So which of the functional groups can undergo nucleophilic attack? Okay, so first of all, nucleophile. So nucleophiles are a species that donate a lone pair of electrons to form a dative covalent bond, right? And meaning that if they have a lone pair, they're going to be a little bit more negative, right? Meaning that they're going to be attracted to something more positive. So they must attack something more positive. So let's look at these carbons. These 2 carbons are attached to a more electronegative atom, so they are partially positive. So bromine and oxygen, these are more electronegative atoms than carbons, so they're going to draw the electrons toward themselves from the covalent bond that they have, okay? So making the carbon there a little bit more positive, meaning that they're going to be susceptible to the attack of nucleophiles, right? If you see Y, though, on the carbon-carbon double bond, the electron density is going to be very high, so it will repel away the nucleophiles, okay? So, yeah, it won't be susceptible to the attack of nucleophiles, but they will be susceptible to the attack of electrophiles, right? The ones that will accept a lone pair of electrons to form a dative covalent bond. Okay, so the answer is going to be X and Z only. Okay, and question 15. What is the formula of the pale yellow solid formed when propanol reacts with iodine in the presence of sodium hydroxide? So this is the iodoform reaction. So alkaline iodine, sodium hydroxide is alkaline, right? Alkaline iodine is iodoform reaction. And the pale yellow precipitate that forms, you have to memorize this formula. CHI3 is going to be your positive result, okay? And they test for the methyl ketone group, right? And propanone has a methyl ketone group, okay? And also, in addition, this carbon can be an alcohol group, okay? So this can be a methyl bonded to a C and then OH, okay? So that is question 15. And question 16, butanone can be distinguished from butanoic acid by the addition of. So we're going to try and differentiate between butanone, which is a ketone, and a butanoic acid. Okay, butanone, a ketone is a carbonyl group, right? A butanoic acid is a carboxylic acid group. So it's a carboxyl group versus carbonyl group, okay? Feeling solution and Toland's reagent, these both test for the aldehydes, okay? So feelings, it starts from a blue solution and then it gives a red, brick red precipitate if they come in contact with aldehydes. And with Toland's, you get a silver mirror, right, with aldehydes. But we don't have aldehydes, we have ketones and a carboxylic acid. So A and B are incorrect. And if you look at D, acidified potassium dichromate solution and refluxing. So this is an oxidizing agent, right? And what do we know about ketones and carboxylic acids? They are fully oxidized already. So they're not going to further oxidize, meaning that the color of potassium dichromate, which is orange, is just going to be remaining orange for both butanone and butanoic acid, okay? You're not going to see that color change from orange to green when oxidation occurs, so you cannot distinguish it. And with C, 2,4-DNPH, dinitrophenylhydrazine solution, this is a test for carbonyl groups, so for aldehydes and ketones, okay? And the positive result is going to be a yellow-orange crystal. But we know that butanoic acid is a carboxyl group, not a carbonyl group, so it's not going to test positive. So with using 2,4-DNPH, we can distinguish the difference between butanone and butanoic acid. Not the difference, but we can see that we have two different compounds, okay? So yeah, that's C. And 17, which could be used to make CH3, CONH, and CH3. If you just read that, it's a little bit difficult to, figure out what that actually is. So it's better to just draw it out, okay? Draw it out and you can see that this is an amide, okay? Meaning that for an amide to form, you either need basically carboxylic acid and an amine. In this case, it should be a primary amine, right? And you could also use ethanoyl chloride in this case, and a methyl amine, right? If you break the amide, you can tell that you need those compounds, and so therefore the answer must be D, okay? And the other options just, you can't form it with the other options. It's quite obvious. This is quite an obvious question. So question 18, which reaction may be used to make a carboxylic acid in a single step? Okay, so we're gonna look at B first. Hydrolysis of an ester with sodium hydroxide. This is going to give you a salt. So you're gonna get this first. With an ester, you're gonna get an alcohol and this, a salt, ionic salt. So this must be followed by acid hydrolysis in order to basically protonate this ion, this, carboxylate ion, okay? So no, that is 2 steps and it's not a single step. And question C, the choice C, reaction of acidified potassium manganate, KMnO4, with an alkene. This is going to form a diol on the carbon-carbon double bond, right? So it doesn't form a carboxylic acid at all, so that is incorrect. And with D, reaction of an acyl chloride with ammonia. So this is going to be forming an amide, right? Just like in 17, we formed an amide using an acyl chloride and in the primary amine. And this over here is ammonia, which is just NH3. Therefore, you're just going to get a primary amide. Over here, you have a secondary amide. But yeah, so D is incorrect. You're not going to get a carboxylic acid. If you look at A, hydrolysis of an ester with hydrochloric acid, that is acid hydrolysis of the ester, right? So you're going to get a carboxylic acid group and an alcohol, okay? So that is a single step process. Therefore, A is going to be your answer. So I was a little bit skeptical about this one because, you know, if you hydrolyze it with hydrochloric acid, you're gonna get, you're gonna have hydrochloric acid in there, you're gonna have the carboxylic acid, you're gonna have the alcohol, you're gonna have the not unhydrolyzed ester in there as well. So technically you need to have another step of purifying it and extracting just the carboxylic acid. But oh well, A is closest to the answer of a single step. Okay, so question 19. The mass spectrum of ethanoyl chloride could not be expected to have a peak at the ME mass charge value of. And we have all of these choices. So first of all, I just drew out what ethanoyl chloride looks like, and I'm just gonna label all the masses down. So if we have 3 hydrogens, each one weighs 1, so I just wrote 3. Carbon weighs 12, and then oxygen weighs 16, and we have chlorine, which can either weigh 35 or 37, depending on which isotope it is. So therefore, straight away, you can see that A is incorrect, because you can't have half a neutron and have a 35.5 isotope for chlorine. So obviously A is the answer. But yeah, it's obvious if you know that there cannot be a 35.5 isotope for chlorine. You only have 35 and 37. But if you look at the other choices, it's obvious that they are possible, because 37 is your 37 chlorine isotope when you break this bond. And also, if you break that bond, you're going to get this fragment, which is the H3C, C, double bond O, plus this fragment, which weighs 43 if you calculate it. 12 plus 12 plus 16 plus 3 is 43. And if you look at 78, this is the molecular ion peak when you have the isotope 35. Okay, so B and C and D are all possible peaks. Okay. So yeah, 19 is A. With 20, a ketone which would not be expected to have a peak in its mass spectrum at mass charge ratio 57 is, so we have the choice compounds. We have butanone, 3-methylbutanone, pentanthreone, and hexanthreone. So we need to ask ourselves, what fragments can we have, okay, in these compounds? So with butanone, I just drew out the displayed formula. I was lazy to draw all the hydrogens, but you get what I mean. It has a bond, so it's bonded to hydrogen. So if you basically try and just, break that bond, then you get this fragment with a, formula of C3H5O+. That is going to have a mass charge ratio of 57, okay? So butanone has a mass, the peak at 57, and this can be your reference for looking at the other compounds to see if they have the same fragment. Okay, so with C, pentanthreone, I just drew it out again. It has that C3H5O+ fragment, and also in D, it also has the C3H5O+ fragment, but in B, you cannot see that fragment, okay? So it's because, this has to be just CH2, CH3, CH2, and then CO. This has to go somewhere else, right? If that methyl group is there, you cannot make that fragment C3H5O+. So therefore, the answer is going to be B for 20. Okay, so yeah, that was the whole of section A, 20 questions, 20 multiple choice questions. So they didn't really have like 18A, 18B, something like that. So it just ended right at 20. Sometimes they have fragmented questions where you have A and B in one question. So sometimes it ends at like question 19 or 18. But yeah, that was just extra information that you probably don't need. But yeah, I hope that was really clear. If you have any other questions in terms of, you know, why is that, and why is that correct, why is that incorrect, why is that the case, you know, just leave a comment below and I will try and get to you as soon as possible. All right, see you in the next video where I cover section B of this same paper. Bye.